Welcome to today's session in module 1.4. In today's session, we're going to be talking about the OSPF, otherwise known as Open Shortest Path First. These are the objectives that we have to cover. Definitely, we will be covering a little bit extra apart from the just basic adjacencies, because I believe you'll not be able to understand what are LSA throttling unless you dive deep into what are LSAs and you know how they actually behave. So today's depends on the availability and the timing. We'll try to cover as much as possible today. So let's get started. If you know about the OSPF, it was a big change in the network industry. It was developed by IETF and was supposed to be open standard replacement of a RIP. We understood its limitation, right? As a pure distance vector, a routing protocol, it had limitations of how further it can perform the routing. And because of that limitation, Cisco came up with their own protocol, and also open standard community started working on their own version of protocol as well. And there are two versions that are active at the moment. We have version 2 and version 3. Version 2 specifically used for IPv4. Version 3 can support IPv4 as well as IPv6 also. Spatial features, if we talk about why OSPF is a big deal, apart from being a link state routing protocol, it's convergence. But I would say I would give credit of convergence to the IGRP. OSPF is actually highly scalable routing protocol because of its native features. It's even if you just enable OSPF and just follow some basic rules of using areas carefully, without too much optimization and tweaking, you have very well scaled OSPF design network, routing network. Because of how the LSAs are created and how the OSPF behaves, right from the point where you enable OSPF on the interface all the way to it's advertising its information. All of that results in a very less likely to be a bad routing to happen. Obviously, definitely, even if you are using OSPF, which all following all the rules, you still may have some problems like suboptimal routing, unintentional routing behaviors. We are talking about some advanced features where you are tweaking the cost, you're performing summarization, and the traffic is going from some border router where you're not intending to go, regardless, anyway. So, but overall, it's pretty good protocol. It's very less susceptible to bad routing information. It uses concept of areas, this a boundary of all the routers that share a same type of information. More on this upcoming slide. It basically reduces, because the way that routing information is routed inside of that areas, it puts less impact on the CPU and resources on that device. By design, it has a fully classless behavior. It also supports authentication, right? Very similar to what we use in ERGRP, but it's not complicated because in ERGRP there was a limitation, right? If you talk about the classical ERGRP, it only supported MD5. If you talked about the named ERGRP, it support MD5 as well as SHA. In OSPF, it has a native support of SHA. And not only just a basic SHA, you can have 256-bit, 512-bit, and not only that, but you can also you can encrypt those using. You can also opt for a plain authentication with no encryption and no hashing, or vice versa. You also have an option for that. Just like tagging as well, here you can also tag your external routes to avoid any routing loops as well. So apart from just if you just cover the LSAs, you'll understand how well this routing protocol is made. We're gonna get started. Very first objective was adjacencies. I've kind of divided it into multiple sub-objectives. We're gonna get started with how the OSPF process initializes, how router ID is elected in different types of packets, its structure, the OSPF headers. We're going to talk about OSPF, or more specifically, hello packet in detail, as per the adjacencies is concerned, and then how adjacencies happen in detail, like what are the difference. Obviously, we're not going to talk about like the basic stuff. We'll try to go as detailed as possible. So if you just talk about the adjacencies, well, you enable OSPF and two routers from the adjacency. That's apart from that, if you just want to get to that point, there are certain things we have to understand before we understand the adjacency process. Okay, let's talk about how the OSPF process initializes. So basically, anyone who wants to initialize OSPF on a specific router or switch, you would type router, OSPF, and the process ID. This is enabling OSPF version 2, which is a default, basically used for IPv4. And this process ID, it doesn't matter. It doesn't have to match. Very similar to how AS was used. And if you're using a autonomous system of VRJAP on one side, it has to match on the other side. Here, it's not the case. This is only locally significant and locally used, and it's not sent to the router. It does not need to match between neighbors. So whatever the, right? When we enable OSPF process, we can use show IP OSPF command to check the process related information. What process are we using? What router ID have been selected, which is a manual process that it goes through, when it was started, and information regarding LSs, how they behave, you know, how the SPF is actually being calculated. And on the local router, what are the things that it supports? You can see it's also mentioning something called, it supports NSSA as well. It supports area transit capability as well. So it basically telling that this router can act like a border router. Many of these things seems like an alienated language for us. We don't have to know pretty much everything, but by the end of the session, you'll be able to understand many of these things, like initial LSA, throttle delay, what is SPF schedule delay, all these things. Why there is a minimum and maximum value in each one, all these things. But idea of this slide is that you can use show IP OSPF to understand process related stuff about OSPF. The very first thing, when you enable OSPF, the process, you haven't enabled OSPF on an interface, but just generalize. When you enable process on a router, it does first thing is that it tries to find the router ID. And without it, it cannot function. Even two routers cannot have same ID. It's going to cause a really big issues in LSAs and the way it's designed. So OSPF cannot function without router ID. Router ID have to be selected. It has to be. First of all, it checks if you have configured any manual ID under the router configuration. A simple command is there, router ID, and then whatever the ID is you want to configure. The logic is same. If you haven't configured, it tries to find if there are any loopback interfaces. If there are multiple in one, it will try to find the highest available loopback interface, and it should be in upstate. Highest loopback, that is in upstate, it will take that IP address because it follows the same logic of an IP address. It will take that loopback IP and configure it as a OSPF router ID. Assuming we don't have a loopback on that router, at least we should have a physical IP address configured. And among the multiple IP addresses, the highest physical IP that is in upstate, that interface IP address will be taken as a route ID automatically. Let's assume, because what happens is, our intention is to assign a manual ID, but OSPF process starts in sub-second, less than a second. So automatically a certain router ID have chosen, and you went inside and you have given it a router ID, let's suppose 1.1.1. You've given some router ID. Maybe loopback was created later, and that loopback you wanted to give it as a router ID. Well, it's not going to choose automatically. Once that is done, it is that a router ID is mapped to the process. We have to clear the OSPF process using clear IP OSPF process command in order to, and it will ask you for confirmation basically, and you have to hit yes. If you just hit, or type this and hit enter, is basically assuming no by default. So make sure that you type yes, and yes, then it will restart again and try to do the same thing. Manual, do we have a loopback, and do we have a physical interface? Assuming we have typed the router ID command, it will take precedence now, and that router ID will be assigned. There is a problem though that you have to remember. It's not intentional, but it happens accidentally or because of human errors. There are two routers somewhere. Your OSPF routing is behaving funny. There are some LSs are showing duplicate, and maybe traffic is not traversing. Something's happening, and you're not able to actually find out what's happening. One other thing you should check if there are any duplicate router IDs. Okay, because router ID is crucial part of the forming adjacency in the beginning of the phase. If two routers have the same router ID, it's going to cause big issues like instability in the adjacencies. If adjacencies have been formed, there's going to be a lot of issues regarding the routing information exchange, link state update, packet, or link state advertisements are going to be flapping a lot. You'll see generally error or something like this, or if you have duplicate router ID errors. Well, logically, you want to change the router ID again, you have to clear the IP OSPF process in order to meet the result. Generally, you're going to see, why do we have loopback interface? And I'm not going to be very clear about this, but the topology that we are using in the OSPF, just try to memorize every single subnet. Just follow the design, and it's not going to be too much of hard work. It barely will take you a couple of minutes to understand how the IP reserve plays. There is one reason. I'll reveal why at the end of the class. So generally, you'll see by the design, many of network engineers or many organizations, when they're using OSPF pretty much everywhere, based on the areas or based on the sites they have IP addressing configured. If you see, this is the DC we are talking about. And here, pretty much every single router have a loopback, and the DC is using 10.2. Generally, okay, when we're talking about 10.2.255, it's a loopback. That means everywhere, or at least majority of the router have selected a router ID from that loopback. Well, it's because when you look at the database, it is predictable which router ID this information belongs to. So if you take out this route, 10.2.255, this is the router 1 we're looking at. This is the routing information router 1. Okay, see, so it's much easier to troubleshoot when you understand when you kind of just remember which router is which, because it narrows down the troubleshooting time. It makes, I would say, day and night difference when you remember which router is which. And you can simply understand, because when we know this is the router 1 and this is not how it's supposed to behave, the way it's behaving right now something is wrong. Because of the predictability, usually people go with designs like this. Secondly, if a physical interface was selected for router ID, if that interface goes down, then what? Right, router ID will fail when the router process will start next time. So loopbacks are stable. They only fail when the entire router is going to fail, right? So that's the second reason why people may go with the low back interfaces. Let's talk about how we initialize OSPF on a specific interfaces. There are two ways we can initialize OSPF on interface: the legacy way, the network command, and under the OSPF you'll be using network command. Network, basically here I'm matching all the interfaces. I don't care about any of their subnet mask. And area 0. So basically this router is matching all interfaces and putting them in area 0. If you don't provide area 0, you just hit enter, it will say it's incomplete command. It will not even accept that command. So by design, you have to put at least one interface in a specific area. In the beginning, we use area 0 because area 0 is what we call as a backbone. Based on the word, you can understand the importance of area 0. Because area 0 plays a big role. Without it, you will not have OSPF definitely. But anyway, the point is, if you enable OSPF on any interface, 1, 2, 3 doesn't matter how many. But if you enable OSPF, it must be in at least an area. We're going to talk about areas more in detail later. Second option we have is the interface level command. The command is IP OSPF, then process ID, and then area ID. Area is a command. These are going to be IDs. So the one benefit here, because if you don't want to use network command, you can also use this. There is no best practices. It's generally when we know by design, especially from the perspective of a person who's architect level, they would usually use a interface level commands. Using show IP OSPF interface brief, we can get the details of how many interfaces are there that have OSPF enabled. This is a table output, show IP interface brief. So definitely more on this information and how to read this. But you can see the first column is telling these are the interfaces that have OSPF enabled. Obviously on router 212, I just went out and enabled OSPF on all the interfaces. That's why we're seeing all the interfaces, including the loopback. Okay. If you want to pick any specific interface and you want to get the detailed information, you can also, using show IP OSPF interface, instead of using brief, you provide the interface name there. It will give you that interface is up, the line protocol is up, what is the address on that interface, what is the interface ID. ID is in the same thing as in the spanner tree. First, this is Ethernet 1/0. This is the 6th interface. That means we had Ethernet 0/0, 0/1, 0/2, something like that. So this interface, in which area it is, what is the network type, what is the cost of this interface. You have different times available. You have retransmit timer, wait timer, date, fellow timers. You have transmit delay available as well. Most important of all, usually you come here to know about the authentication. And it's telling that, okay, you don't see anything here. That means there is no authentication enabled. More on this later. So this is how you enable OSPF. There are two ways: network and interface level command. Once that is done, initially the hello packets are sent out. What are hello packets? Basically, OSPF have a specific structure, okay, that they follow. So this is the packet capture actually. You see here, the OSPF header, we're always going to see OSPF header, regardless of the packet type. There are certain parameters inside of it, like authentication, packet type. These things are always going to be there whenever, not just hello or any other packet. Header is going to be there. The second one, what packet it is, and then packet related information will be inside of it. Like this is hello packet, all the hello parameters will be inside of this block. And then there's going to be OSPF LLS data block. I'm not exactly sure why they use this specific thing, but it's not used specific to enterprise at least. Maybe that's used in, there are some fields like TLVs, maybe used in the service provider, but not specific to enterprise design. So there are 5 packets available in OSPF. The hello packet, you have the rest of them are usually used with adjacency formation, right? In ERGRP, we had similar things available. You had a database descriptor packet or database description packet. There are multiple terms that this packet is known by. Link state request packet, link state update packet, and link state acknowledgement. I'll try to focus on hello packet as the context is relevant to that packet. And then in the next slides, we will discuss about the remaining 4 packets in detail. Okay. In the header, okay, I'm not talking about the packet level information, OSPF, hello, DVD. I'm talking about header itself. That's going to be always with them, this guy. Regardless of which packet it is, it's going to be, header is going to be there. What do we have inside? We're going to see the what version it is. Is it version 2 or version 3? Okay, what type of packet it is? Packet 1 is basically hello packet. Okay, hello is true. The packet length, source, OSPF router. This is the ID and not the IP address. This is the router ID. Okay, OSPF uses its own checksum as well. We're gonna dive deep into checksums later. And then authentication also. Even though we don't have anything at the moment, I barely enable OSPF on router 212. It sent out this hello packet. In that hello packet, header was already attached. So basically, OSPF have 3 types of authentication. No authentication is also considered as a type. Type 0 or null authentication is also considered as a type, which is a default. It's saying authentication type is null, and authentication data, there is no authentication data because authentication type is null. Usually, authentication data holds your passwords, authentication type holds what type of it is. There is a type 1 and type 2 available as well. The plain text and the encrypted password, cryptographic password. But we will dive deep more into it later. So we understood the header on high level. If you talk about the hello packet itself, what are we having? Hello packet serves basically 3 purposes. When you enable it, that interface starts sending out hello packets on that interface. And when it's sending out, it inserts a couple of information. That interface is subnet mask. And it also includes the default, depends on what interface it is. I'm talking about the technology behind that interface. It's Ethernet. Doesn't matter what fast Ethernet, gigabit, but it's major technology is Ethernet. So based on that, it chooses a specific timer and puts inside of hello packet when it's sending. Ethernet technology uses hello timer as 10 seconds. We have some kind of a flags. It's basically, there are so many different flags available. We'll dive deep into it later again in the next class. This is way of sender, which is at this moment is router 212. It's a way of telling that I support so and so things, and this turns on that flag. At this moment, it has turned on, or E flag is set to 1, which is its way of telling I support type 5 LSA, or I support external routing information as well. Why do we have to tell? Because there are certain design considerations. Later we'll learn that in those areas, external routes are not to be advertised. Okay, we will see those. So here they have to explicitly tell in the hello packet, this is also have to match. Okay, if this is not matching, then the other guy is not going to form the membership with us. So that's why they mention the capabilities in some options also. The router priority is also mentioned based on the link. Usually it's 1. I'll talk about the network types because this information is connected or related with the network types. when we have a broadcast type of network, Ethernet is a broadcast type of network. Okay, this is broadcast network by design, by default, because we depends on ARP and flooding, all those behavior. This is broadcast type of design. And here in broadcast network, even though physically two routers are connected like this, it's still a broadcast because technology is broadcast, not a physicality. It's not going to define the network type is defined based on the what is underneath, the technology underneath, not how they are connected. Okay, just remember that. So if it's a broadcast network, you're going to see router priority, which is default 1. We are seeing hello timer is 10 seconds multiplied by 4. Dead interval is 40. Designated router and backup designated router, these are the two routers specially elected and configured in this broadcast type of network. And hence Ethernet is considered a broadcast network. You're seeing designated and backup designated router. Now here's the thing. Even if certain network is considered as a point-to-point network, and these are designated router and backup designated router, these two routers, they don't have to elect. Router still will inject this information, even though it's not going to provide much information. We are seeing very early type of hello here. Nothing happened. Nothing have happened so far. We're only seeing this is maybe first or second hello. Okay, so we will dive deep into these specific things later. But here on this link, I can say this is not a first hello. How? It's basically saying somebody already sent a hello. The receiving router have noticed its router ID, because we know that router ID is part of, let me go back, part of the header. So receiving router have taken the notice that, okay, so and so router, which router? So and so router have sent me hello packet. So when next packet, hello packet is being sent out from this guy who sent this hello, it added that router's ID, right, that router ID in the active neighbor field. Now, it serves a crucial purpose. We will understand it coming sessions. Excuse me, coming slides. So these are the things that are available in hello packets. Generally, if its very first hello packet is sent out, it's serving what? It's discovering the neighbors on that link. And this packet that we are looking at is not a first packet, because now we already have received the first packet. We have taken notice of that router ID, and we are inserting that router ID into our active neighbor field and then sending out. So basically, this is the second packet neighbor. So using this active neighbor, receiving on the other hand, this was router 202, because I can understand based on the loopback 10.2.255.202. This 202 will know, okay, I see my router ID. Somebody sent me a hello, and I see my own router ID in it. That means my earlier hello went to the other side. That's how the two-way communication is established. Using these hello packet also, we elect the DR and BDR as well. Why and how later. After the adjacency has been established, hello packets are still exchanged. They act like a keep alive mechanism. They maintain the adjacency. If we don't receive hello packets for 40 seconds, timer will expire, and then the senders we're expecting the hello packet from, we are going to consider that neighbor as dead. So we see all these parameters are there. Some are inside of a header, some are inside of a hello packet itself. There are certain things that needs to match on both sides. Area ID is supposed to match. The timers supposed to match. Authentications, if used, supposed to match. If on both sides, authentication type 0, then, but still, it should match. There are some kind of a flags. They also should match, very similar to how we have here. So the flags should match. More specifically, talking about a stub. What are stub? It's very different than the EITP stub. We'll dive deep into it later. So we understood we already understood why do we need active neighbor list, right? It's a list of the neighbors which we have received hello from. maybe on that link, this is connected to a switch, and maybe we have multiple routers in there. And this sender router, this guy have received these multiple hellos. When it is going to send out its own hello, it's going to mention all those neighbors it received the hello from earlier. It's going to maintain all those neighbors in the active neighbor list. And when they receive this hello, they know, okay, our earlier hello was sent out to the guy who sent us this hello. And that's how the two-way communication is going to be established. Hellos are sent periodically, regardless whether we have formed the adjacencies or we are forming the adjacencies. Yeah, we are in the process. Unless we make that interface as a passive interface where we are suppressing hello, that's a different story. Sender, as in, this is act. So some which is asking here that active neighbor is the sender's router ID. No, active neighbor. When I said, let's assume this is router 201. The sender is 201. In short, it was connected to 202. Earlier, what happened? 202 sent the first hello. 202 don't have anything. Its active neighbor field was 0.0.0.0 because its own first hello is being sent out. 201 received it. It's noticing in this hello, the router ID says that it's 202, 10.2.255.2.0. When it's going to generate its own hello, it's going to inject that router ID in that hello, and it's going to send out towards route 202. It's not senders. It's actually from the sender's hello, instead of sender's hello, they're injecting the router ID of the guy who sent OSPF hello earlier. It's to tell them, hey, I received. Hey, 202, I have received. Who's telling? 201. This guy is telling to 202, I have received your earlier hello that you sent me. When 202 receives it, it knows, okay, my earlier hello that I sent out, it is received and the guy is replying back. It's kind of acting as a reply in this case. Okay. So hello packets are sent out periodically, depends on the network type. Ethernet, it's 10 seconds. If you have a non-broadcast networks, it's sent out 30 seconds, like non-broadcast multi-access NBMA networks. If we can also change the timers on an interface level basis, IP OSPF hello interval can change this. We also have a data interval by default multiplied by 4. It is shown in the hello packet itself. This there is based on the RFCs. Actually, they are called hello interval and a router data interval. So Cisco's router data interval is 4 times the hello interval. Here 40 seconds, and if non-broadcast network, it's going to be 120 seconds. We can change the date timer as well separately. IP OSPF date interval on any interface that you want to maybe fasten the process of neighbor detachment. You have all sort of things. You have BFDs, you have fast hellos as well. Okay, we will see that in coming sessions. Now let's talk about the adjacency formation. I'm taking a really basic example of 2 routers to understand the adjacency formation process. Feel free to ask me any questions if you guys have any. Okay. So we're going to use these 2 routers. We have router 211 and router 212. These guys have 10.2.255.211 router, 10.2.255.212 as a router ID. So basically, the idea is that on Ethernet 0/2 on both interfaces, you have configured OSPF. Immediately when we configure OSPF, it's not fixated which router is going to send hello first. But here, to understand the process, we're assuming that router 212 This guy have sent the first hello type 1 packet out to Ethernet 0/2. It added its source IP, destination is a multicast address 224.0.0.5. This is the first OSPF multicast address they are going to send this packet on. And then active neighbor list is empty, 0.0.0, because this is the very first packet. Nobody sent us anything earlier. So we're not acknowledging anyone. The process is still in the down state at the moment. No init. Router 211 on this side, it was down earlier. Router 211 have received it have received this hello packet. What router 11 does, it's first of all going to check those parameters, timers, area, the authentication. If it's a stub area, it's going to match. It's going to check the stub area flags as well. If that is matching, from down to, it's going to change the state to init. And then router 211 is going to know first hello was received here. It knows that router 212, 255, 212. This is the guy who sent me hello earlier. So when the next hello is being sent out, it's adding as an active neighbor in the hello of this router 211. It's sending the same hello out to 224.0.0.5. In that hello, look at this. This is the hello sent from 211. Active neighbor is added 212. The rest of the things is supposed to be pretty much the same case. Like, what do we got? Active neighbor. They didn't elect the DR PDR yet because this is earlier stage at the moment. If you check router 12, router 212 is going to receive that hello at the moment. It's going to look inside that hello packet and sees that, okay, it's my router ID in the active neighbor field. And that means router 211 was sent me this packet, can hear me. And this is how router 212 directly from downstate is acknowledging, okay, it directly goes through two-way state. Now, build on the documentation. Or some documentation, I understood that it first goes down to init state, but actually router 212 here goes to down because hello received with its own router ID. It's going to directly to the two-way state. And then next hello is going to send out, in which active neighbor is going to be 211. This guy also knows about it. So what it does, from down to init and from init to two-way state. So two-way state only happens when they receive a hello packet with their own router ID. And then two-way state goes. 212 is sending a packet. It's adding the active neighbor router 211 there. So both parties at the moment are in the two-way state. Now, there are two things going to happen at this specific thing. Okay, at this state depends on the network type. I told you this is Ethernet. Okay, I acknowledge that. I told you, but I made these line already as a point-to-point. I have manually configured them point-to-point because we haven't talked about the network types. I want people to explain in detail what DR and PDR relation does. We will be getting away from the points that we want to explain, we want to talk about. So assume that these are the two point-to-point link, and then when I'll talk about the network types, we will come to two-way state again. What happens at this stage before moving on to the next stage? What happens with the types that are broadcast networks? But I made already point-to-point. So from two-way, they're directly going to the X start state. So I would say, from the perspective of any distance vector routing protocol like EIGRP, they have formed the neighborship. They have formed the adjacency. Now they need to sync the database. They need to send the routing information. OSPF have very different type of routing information. They don't have a one routing info. They call that routing information, not a packet type. They call that info link state advertisements. And there are many types of advertisements. That's how it is. So if with like 50, 60 routers is going to be a huge database, and it's not, it just can't send that in a single packet. It needs to be fragmented based on the MTU value as well. So a couple of things needs to be decided before we sync the information, right? Because they need to agree upon, they need to keep the track of how many packets they're sending, that routing information of packet they're sending, and what are the sequence they are keeping to that, because they need to keep track of it. Why it matters? Because it matters because we can't send the whole information in a single packet. It's going to be fragmented based on the MTU value, and each packet that we are sending is going to be synchronized based on the sequence number. What sequence number? I'm not talking about the IP headers here. I'm talking about OSPF level information. Here, router 212 and router 211 both are going to send each other the second type of packet. Hello packet's job is done now. It got us until the two-way state. The database description packet, the DBD packets here are used in two different scenarios. The first one, right after two-way state, both parties exchange the empty DBD packets. Empty database descriptor packet, description packet, or descriptor packet. This is how it is. This is what inside of a database description. You see, just like very similar to how OSPF hellos had, this guy also have options. But I want you to focus on this and this. So we have a database descriptor packet. Inside of it, we have a specific flags in it. We have three flags. We have init, we have more, and master flag. Here's the thing. What happened here, as soon as two-way state went, and in the further state, they are sending each other the DBD packet. In that, they are also presenting a sequence number. So both parties, both sides are going to claim they are master. In extart state, a master and a slave needs to be elected in order to track the information. Because if they're not going to have agreement upon what sequence number they should use, they will not be in sync. So in order to become sync, in order to exchange routing information further, before let's decide who's going to decide what sequence number is going to be. So both say I'm going to be okay, sure. So both parties says I'm a master. Both gonna send the same DBD. This is the empty one, by the way. It doesn't have any specific information. It says, hey, I'm master. Okay, and this is MS bit. Okay, MS bit set to 1, and it's presenting a sequence number. This is a sequence number I should use. We should use. This is what it's saying. So router 211 is sending a sequence number 88866. Look at this. And it's saying I am the master. Router 212 is sending 2996, and I am the master. But the router that have highest router ID. Yes, Vijay, go on.
So can we go on the previous slides, two more slides back, where you was checking this thing, the hello, the init and two-way. See, so what happened? Like, as I understand, like, so router 212 is in both routers are in down state, and router 212 will send a hello to 211. After sending the hello, it will be like both are in down state. After sending the hello, router 211 acknowledge the packet that router 212 has sent, and it will become in the down to init state, and it will resend the acknowledgement packet to router 212. The router 211 will be like from down to init state, and 212 will become 212 init to two-way state. Then how like the router 211 will go into the direct it will be going direct
No,
extra.
listen,
So
listen,
how
listen.
to go?
Are you with me when I said to the point where I said that this guy? Do you understand how this guy got to two-way state?
Yes,
Now this guy is still in init state. Okay,
yes, correct. Yeah.
it's still sending its own hello packet. All
Mm.
right,
Mm-hmm.
router 212 is sending hello packet, but now it's in two-way state. It has seen a hello packet from this guy with its own router ID as an active neighbor. It is also sending its own hello packet. And what is inside here? Active neighbor is whom? What is this?
The 211.
Right? So when this gets back here, from init, it goes to two-way state as well. So both parties on here, without two-way state, they can't go back. They can't go further. So both parties have to be in the two-way state here in this case. You understand?
Yes, yes.
Okay. From two-way state, they are going to extract state. Now before they exchange this huge load of routing information, they are electing who should become the master. Because because I explained, right, it's going to be big information. It's going to be it needs to be fragmented based on the MTU value, and it needs to be fragmented. OSPF design internally have this operation where they keep track of how many fragmented information they have sent. Okay, so this needs to be tracked using a sequence number. Who decide a sequence number between both guys? Who's going to do that? Who is going to do that? So here, excuse me, where will be here on this slide? So both parties, they do what? Hey, you know what? I'm supposed to. Both parties exchange the DBT packet. Please understand this, okay? It's
Yes.
very information. When I said both are exchanging DBT packet, but not just any DBT. These packets, this is the second type of packet that is empty packet. There is nothing inside of it except some claims that they're making. What are the claims? Router 211 says I am master by setting the MS bit to 1, and it's saying we should use, because I'm the master, I'm thinking I'm a master, so we should 8866. This is the sequence number we should exchange the routing information from. Router 212 says, you know what, I am also a master and I present 2996.
It's a randomly selected sequence number.
This
Correct?
is the randomly selected. There is no specific logic behind it. This is that randomly selected number. But what happens is they compare each other's router IDs. Okay, and both parties have understanding. Okay, both parties are smart enough to understand among both guys which router have a higher router ID. Obviously, router 212, right? 10.2.255.211 and 10.2.255.212. Which one is higher router ID? 212 is a higher router ID. Automatically, this guy becomes a master and this guy becomes a slave. Okay. For further routing information, remember that 212 presented this sequence number. It said we should use 2996. This is what it presented in that empty packet. A very important information. This is the exact moment you guys remember, right? When it's in CCN or CCNP practice, we remember that when empty values don't match, OSPF neighborship also doesn't come. It's stuck in its extat. You guys remember that? Anybody face it?
Yes.
Right? Do you see what's in here?
Yes, at 1500 MT.
I told you about the fragmentation. I talked about the empty values because information needs to be in sync. Empty value needs to be matching here, right? Otherwise, it wouldn't know if I have, how can I explain? If I have, let's say, I have 100 routes. I don't know. The first packet that I'm sending, router 1, have, this is router 2. This guy's MTU is, let's suppose, 50. Okay, other guys have 40. Then we're going to form the neighborship. This is not realistic, but I'm just explaining a simple value. I have 100 routes to send. You know, it needs to be very quick. we are not going to play around. My value is my MTU value is 50, so my neighbor should send me two packets. First packet should contain 50 routes, second packet should contain 50 routes. It's not like that. They are not keeping room for calculations there. Rather, they're just simply playing one rule that both parties should have the same MTU, because that's how here they know. If this is not matching, they're not going to form the neighborship. They're not going to move. Adjacency is going to die right here.
I've seen one scenario where one side is jumbo MTU is configured 9,000 and one side is 4996 MTU was configured, but the
Okay.
neighborship was up.
Then you as an admin, you know what you're doing, right? Right. You know that. Okay, this is a scenario. I can't mess that, and I have to make sure that OSPF also comes out. So in that interface, you have a command to ignore the MTU. You say IP OSPF MTU ignore. So neighborship will come up regardless. If you know what you're doing, under that interface where you have OSPF on both sides, you're going to say MTU ignore.
The command was not there, but I don't know how it was happening. I did the dig down also, but nothing.
Where did you check?
Sorry,
Where did you check that?
no, I didn't
What
remember.
what was the platform?
It was the nine catalyst nine.
It's a switch.
No, 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 not a switch. Sorry, ASR 903 and 907.
Okay. Many times, here's what I'm assuming. Okay, I don't know because I haven't. In order to actually explain you why it's not showing, I have to actually look at it.
I was
I
also
have
confused in
hands
that
on.
time at that time, but like the MTU was that ignore command was not there. But one side is Jumbo MTU was configured 9,000 and another side is 4996 like that. It was configured, but the neighborship came up, and that ignore command was not there. I was still wondering how it was working
You are
because
the one who configured that
no, no,
OSPF.
no, it was like working scenario. So
Well,
like
I think, okay,
customer
based on the
log,
documentation, it's not supposed to
yeah,
be
correct, correct,
working.
correct.
And secondly, MTU ignore command should be there. Okay, it's not. Then I'm not exact. I don't know how to answer that because I don't have. At the moment, I don't have access to that device, right? So
No, no, yeah,
it would be incorrect.
I got your point. I've seen many scenarios where theory or in production scenario where theory is failing. There are lots of scenarios I've seen.
Yeah, but I'm explaining you the documentation perspective.
Yeah, correct.
So, and here's the thing. This is also one cool thing that happened. Is that this communication, the whole communication, right after two-way state, this was being done at the unicast. You can see they're directly exchanging this information instead of OSPF multicast packets. They were doing this at the unicast level, right? The destinations are unicast. So now we understood that 212 is our master in this communication, and it presented 2996. This is both side agreed upon. Okay. Now the next step, they go into the exchange state. Extract was to only specifically elect the master and slave. In exchange state, as you can see, the first packet will be sent out by the master. Master is going to send the DVD packet and is going to contain all the LSA. Here's the thing, okay? LSA headers. This is not even the full information again. This is only enough information. This is enough information that receiving side can judge if it needs it or not. Does it have that information in the routing table? If it doesn't have, then it will ask it later by different specific packet. Again, this is the DBD packet. Earlier, the empty packet was used in extract. This is again a DBD packet. And then in this DBD packet, database description packet, you have all the LSA routing information headers. Think of it like instead of full information, it just contains that header information of that routing information. Based on the receiving side can judge if it needs that information or not. It can judge if it has that information or not. Look at the sequence number 2996. So basically they use that. This specific packet that I captured was from the slave. Or how I know? Okay, you can also find it out based on the flags. you should always have MS flag here. It's only have a more flag. This shows in the slave MS flag. So slave is using the same number. How? It should be using 2997, right? Okay, the way it works, basically the master is going to send a DBT packet and it contains the LSA headers. All these are headers only of the full information. It's a summarization only. And the master is going to use the actual sequence number. The slave is going to receive that information, and slave also using the same sequence. Look at it. There is no MS flag set. It's only more flag only. This is the actually slave's packet. So slave is going to receive that packet, DBT packet from master, and slave is only allowed to send. This is important. Slave is only allowed to send the DBT packet in direct response to the master. So master is going to send a packet with a sequence number 2996. Then only say slave is going to send another its own information with the same sequence number. It's like they're being very careful here. This is because why it's so this guy, the slave's packet with the same sequence number is treating it as an acknowledgement to the earlier packet, because otherwise OSPF, the ITF would have need to create another acknowledgement packet for this DBT packet. So it's serving two purposes. By only sending a packet when master sends, slave sends its own packet, own DBT packet with the summarization of the whole routing table it knows. It's using the same sequence number. Master knows my earlier packet went to the slave because I see my own sequence number in there. The next packet I'm going to send, because of the specific MTU value, the next packet will have 2997. If slave needs to send it information, it's going to send. But this is slave, this is captured on the slave also. Even if, let's assume that master have sent one packet and 2997, this is the next packet, and it had some information in it, some information. Say slave received it. Even if slave do not have any data remaining to send, it's still going to respond with an empty DBT with the same sequence number. So it's acting like it's serving like an acknowledgement for the DBT packet. And so it's like, you know, the summary of exchange state is what is happening. The whole, the routing table as a whole, the database as a whole, the master is sending to the slave is sending the whole database to the master. It doesn't matter what they need or not. I'm sending you the summary. It's not going to cost me much. I'm just sending you the summary. And now, based on this, you tell me what you need. They go into the loading state. They go into the loading state. So if a router looked at the DBT headers, okay, the database headers, and realized that, okay, my neighbor has so and so LSAs, and I don't have some, out of all the LSAs that is saying, okay, this one I don't have. The receiving router knows it doesn't have this. What it does, the first packet is sent under the loading state is a link state request. Okay, we talked about the hello packet in detail. We talked about the DBT packet in detail. We're talking about the link state request packet, LSR. So in the LSA, it's not going to, now LSAs are link state request packets serve only one purpose. Out of all the DBT information we received and we figured out what we want, it's going to be asked specifically inside of the link state request. And only enough information, again, only the headers are going to be in there so that sender would know what it needs to send. Here we have asked type 1 LSAs of router 6 and router 212. The sender guy is sending it responds with the fourth type of packet, type 4 packet. This is the link state update packet. This is an interesting one. Now, if you compare a DBT packet, perform a packet capture on a CML, and see the DBT packet and check the update packet. Here you only had headers. Here you will have header and then remaining link state information related to that LSS as well. I'll explain you how to. I'll teach in a moment how we can interpret LSS and what each line means. But in the update packet, we're not only sending hellos now, we're sending detailed information of what have been asked from us using link state request packet, and we're responding with the link state update packets. Now it contains the full routing information that can actually go into the routing table. This is update. This contains an update packet. Update is a packet, link state update. LSA is not a packet. LSA is information inside of an update packet. Don't get confused. LSU or link state update or simply update packet contains the LSS, link state advertisement. It's the routing type of information that OSPF understands. Now, this is an important information. And for that, we needed an acknowledgement for that. The sender sends back whatever we have received. Okay, it sends back an acknowledgement. And instead of sending the full routing information back, it simply sends the headers of those LSS we have received. And this contains simply the headers. This is what a fifth packet we have. This is the link state acknowledgement or LSAC in short. Link state acknowledgement. So in it, or earlier we had down in it, I'm only talking about the Ethernet type of network. We're not going to see the legacy networks. There is one more state here. I don't even remember that. But down in it, we have two-way. We have X start. Then we have exchange. In X start, we exchange the DBD, master slave. In exchange, three packets are exchanged. LSR, link state request, link state update, and link state acknowledgement. Lastly, XR exchange and loading information is there. And last but not least was done. So loading, did I say it correct or said wrong? Anybody? You can correct me if I said something wrong. You guys not paying attention? Extat, master slave. The same DBT packet is used, but this is empty packet. In the exchange, DBT packet is used, but this contains the summary and this full information. Excuse me, this is summary information of all the essays. In the loading state, we exchange link state request, link state update, and LSAC, link state acknowledgement packets. So we understood DBD, link state request, link state update, and link state acknowledgement, and hello packet. Hence, you have only five packets. You don't have anything else apart from this. Lastly, we have a full state. What is the meaning of full state? It means both parties don't have any information to exchange, and both sides database is in so much sync that there is no slight change apart from the age or some computation inputs. Pretty much everything is synchronized. So now what happens? So full state happens. Now the SPF algorithm is going to run to decide which path is best, and they do it based on the cost. Here, cost is not supposed to be the de facto standard metric. There is no metric used in the original papers in RFC. Cisco said we're gonna still use cost anyway. So yeah, that's the adjacency. Let us take 2 minute break. Uh, my daughter is crying. I want to check with her. Just a moment. I'll be back, please. You're back, guys. So that's what we covered adjacencies. Anybody have any questions? Anyone?
No, I'm okay.
Rick,
No.
Bernard. Okay, if you guys have any questions, please do let me know. Let's talk about the areas. OSPF v3 specifically, we're going to talk about totally after completing OSPF version 2. And network type is also going to be taken in the next sections. We're understanding area types. Okay. So these are the things that specific to areas that we're going to understand. Even though we're going to cover the area types here, I'm not going to talk about the stub areas or stub area, all these things, because for those we need to build the fundamentals of LSS. So we're going to focus mainly on LSS, apart from understanding areas. To understand the cost, how it works, how the flooding mechanism happens, right? What is the LSA flooding, and types of LSAs. And if we get time, let's hopefully cover the summarization as well. Summarization is a little bit topic in OSPF, but we'll give it a time. So the SPF itself was not designed to put, it's not itself is resource intensive, okay? But the flooding mechanism that we're going to see, the way LSS are flooded after such some interval, and I told you it's not only one routing information, there are multiple types of LSS. This behavior, the way they are flooded, can put burden on the CPU. So originally, OSPF uses areas to reduce those adverse effects, because the way they work is that if you have certain area, obviously, definitely by default you're going to have area 0 in the beginning. So all routers in that area will have very detailed database information. They know about it, their links, they know about the state. Even though it's a link state protocol, I would say they don't know that much information about the routers that are in the other area, except some exceptions, specialized routers that are called as the border routers or area border routers. So, because as the area will grow, if there is only one area, it will have the same limitation as the EIGRP also have, right? It's not very scalable in design. It is highly convergent routing protocol, but it's not highly scalable. What makes OSPF scalable is less routing information to be maintained because of areas. Routers in this area only they need to worry about the detailed routing information and detailed database information of the same area routers. By definition, area is simply a logical grouping of OSPF routers, or I would say links, because a whole router can be part of an area, but also a router can also be part of multiple areas. This is especially border router, okay? Area border router. We're going to see that if all these routers, this area 0, they exchange this information, they go through a adjacency process, they exchange the link state updates, they have these routes into the routing table. All the routing information shared from the same area, they are considered as intra-area routes. They are the packets, they are the traffic that is consists of traffic between the same area. If a route has been passed through an area with the help of that ABR router, now source was area 0. Now in other area 1, that information came, it became a route from other area, inter-area route. Then we have not only area, I would say totally different source. Maybe you're bringing in routes that are from other OSPF process, or maybe EIGRP process, EIGRP, BGP. You are bringing in those routes in the domain. Those are considered as an external routes. So when you configure area, you have option to configure simply area 0. Now you have a huge number available. 1, 2, 3, you can configure the way you want, or you can also configure area IDs in the designs of IPv4. When you make a routing domain of OSPF, the early routers, the main area, like maybe a regional hub or data center or headquarters, you make those areas as area 0, where all the different branches are going to come a central area, because it works. OSPF works in tier 2-tier design. It doesn't have like hierarchical 3-tier design. It's all the other areas must come to area 0. That is exactly why it is called as a backbone area. The job of area 0 is to summarize all the information. They must travel via area 0. There are some exceptions, and you can overcome with those limitations using things like virtual link. But apart from that, you will not have working OSPF design if you're just saying, I will have this area, will configure area 1 plus as is. I mean, the way OSPF is supposed to work, you will have area 0 first, and then 1, 2, 3, something like that. I explained the area border router. This is the guy who sits in multiple areas in the middle. One link, at least one link will be in the area 0. So based on the definition, that's how it is. Internal routers are your routers from the same area. Backbone routers, they are the routers specialized. They're from area 0. The router was performing the redistribution, bringing in routes from the other sources. There will be a router. This is not just any border router, but this is autonomous system, the process level border router. This guy is basically going to bring in a lot of external routes. So any router to become external router needs to bring in at least one route that is from external source, needs to perform the redistribution. Connected, static, ERGRP doesn't matter, or from other OSPF process. It needs to perform a redistribution. It becomes autonomous system boundary router, and it also lets other routers know that it has become autonomous system boundary router as well. So now we are moving towards the LSAs. We're trying to understand that OSPF is a link state routing protocol. Okay, but apart from what exactly does it mean, right? It is concerned with the links and state of those links, not so easily understandable. So basically, in OSPF, each link has its state, it has its specific type. And just by looking at the LSA, okay, if you understood LSA enough, even without looking at the whole topology, you can design the topology. So this is how it's connected, this is how it's connected. Just from looking at the LSA, if you take out any one router from the area 0, you can, majority of the network you can design just by looking at LSAs. That is how the LSAs are created. So very first thing what every single router does is that when it initializes OSPF on the local interface, it looks at its own interface and initializes OSPF computation on that router. It sets certain parameters on that interface. If you look at show IP OSPF interface, we have a couple of things. What do you get? Okay, we have the interface name. It is in up state. The line protocol is up. We are seeing that this is the IPv4 address on that interface. This link is in area 7. The process ID 1 is running here. On the whole router, we are, for the process ID 1, we are using this router ID. The network type is point-to-point. Forget about the other cost. I'm talking about the local link, the router, when we initialize it, and first look at its own interface. The cost is 781. It's because of high cost is because of the serial links. We have something called transmit delay also. We have transmit delay, and that is 1 second. What is transmit delay? Transmit delay, I would say, when you send out an LSA packet out to an interface, upon seeing this is a 1 second. So that LSA that you sent out from this interface, it's going to age by that number you're seeing. It's 1 second. So it's that LSA sent out from that interface is going to be aging each second, incrementing its age by each second. So every second is going to change. So this is the default actually by design. Excuse me. Thank you. So we have, this is state is point-to-point. Okay. And when I say link state, okay, look at this. This is, it's actually referencing to the local link state is point-to-point, considering that local interface is point-to-point. We have hello timer intervals configured. Hello is 10, dead is 40. Wait, based on the documentation in TCP/IP volume 1, if I remember correctly, this was supposed to be how long they are going to wait in the broadcast domain for if the DR is not responding, basically BDR is going to take over after that time. Okay. Excuse me. The retransmit timer is used as it's going to wait for 5 seconds for acknowledgement, and we're going to retransmit the update packet that haven't been acknowledged. So that's basically, retransmit interval is 5 seconds. What do we have here? Hello is this value is going to change every single second. Hello due in 7 seconds. It's working in reverse order. I'm expecting a hello packet in 7 seconds, 6 seconds, 5 seconds, every second. It's going to change. We have one neighbor count. Adjacent neighbor count is 1 here. Now, why? This was a little confusing for me when I actually saw this. Why mention 2 times? Basically, when you have a broadcast network and you have 5 routers in that network, you may have multiple routers in that network, but adjacent neighbor, the actual full neighborship that you have formed with only with a DR and BDR. That's why. And you have formed with this guy, neighborship. Adjacent router is with this neighbor. You have formed the neighborship with this guy. Neighbor count may be multiple routers there available there. And this is going to help you with the troubleshooting as well, because you may come here to check the unless advanced OSPF configured. You may come here to check maybe the network type. You have to make sure that neighborship is not coming up. You want to check the timers. You may want to check the authentication if used. If the authentication is used, it's going to mention here. This is a message that is MD5 is used, type number 2. And they're also mentioning what key they have used. So that basically you have to go to a specific keychain to find out what actually the key string and what ID they have used. So this is basically telling you the same thing like that I explained. What is IP address, area ID, process ID, router ID, network type, cost. But we have covered more than what I talked about. Transfer delays was cool. We will come back to this to understand that LSA throttling and LSA SPF tuning, all those things. So now the understanding the cost was fixated based on the interface link speed. Okay. How? Basically, they use 100 Mbps as a reference bandwidth, or I would say simply 10 to the power of 8 divided by interface bandwidth in bits per second. Okay, 10 to the power of 8. Now, this was a fixated number. If you have really, when we designed OSPF, we didn't think we would be having interfaces of 10 Gbps or maybe more than 10 Gbps. Max, we thought, okay, 1 Gbps would be like, wow. Anyway, if you consider that limitation, and if you divide it with each interface bandwidth, 10 Mbps in bits per second, you're getting 10 as a cost. Fast Ethernet, you're getting 1 as a cost. Serial link, you're getting 64. This is why we saw serial link. This is not serial link. You are seeing cost 781. I don't know. Let's skip to Ethernet. 100 Mbps, 1 Gbps. Well, we can't use frictional value, so we will come down to 1 again. 10 Gbps 1. Problem with this is that we will not be able to perform actual what is that? Routing selection, right? You may have, if a router may have one path that have maybe like 10 Gbps link and 1 Gbps link. I'm giving you a really small example. This router is thinking the cost for both routers as same because of the limitation in the metric calculation. It's not very complicated. 10 to the power of 8 divided by that interface speed in bits per second. Whatever you get is the cost. You also have an option to change the reference bandwidth in router OSPF configuration. You can change that, right? The reference bandwidth was a higher bandwidth was calculated to a fraction of 1. This is what we understood here, fraction of 1. But fraction was not allowed. So any cost that is calculated to fraction of 1 is rounded up to 1. Cisco gave you option to, Cisco provides the command to auto cost the reference bandwidth, which allows the default reference bandwidth to be changed. If you want, this is the command, auto cost reference bandwidth. So from 100 Mbps, you can maybe increase the bandwidth. You only want to use in a networks where you think is going to be having a bottleneck because of this specific limitation I explained. Okay, I explained the infra transit delay. This is the same thing. Okay, there you go. The transmit delay based on the RFC design, it's called inf or INF trans delay. This is the second by which LSs exiting the interface will have their edges incremented by. Let's just by default is 1 second. But if you're thinking of changing that, you have to change it pretty much everywhere. You have to. The router priority we will talk about in detail, but this is the 8-bit integer. By default, it's going to be 1 on interface. On point-to-point interfaces, this value will be setting down to 0 because router priority is used to elect the DRs and BDRs. But if you're not using any DR, BDR because you don't have a broadcast network, you have point-to-point network, automatically, when you configure any interface as a point-to-point, the priority will become to 0. It will be shown in the. We have it pointed. This is the point-to-point network, so I don't think we see here. We understood authentication type, authentication, right? Now let's talk about the LSA flooding behavior before we move into the lab. So all these LSAs, considering that all these have formed the neighborship, they all have formed the adjacencies, full adjacencies. Now, their job is to maintain the routing. Yes, Bernard?
No question. My bad.
Okay. Everyone is following me so far, right? Am I moving too fast? Everyone, please acknowledge fast.
Are you good?
Okay, cool. So whenever any change is going to happen in the topology, the router's job is to notify to their neighbor. Flooding is the process how they are going to notify, how the new LSAs are going to send out. Because if the previous information was shared and some change happened now, and I just need to send another information, there is some mechanism inside of those LSAs. Please don't get confused. I'm not talking about packets. I'm talking about update packet information, which is link state advertising. LSAs have certain things inside which is going to tell the receiving end, this is the new information, you should process it first and dump the older information. Flooding uses two packets. To achieve the flooding, we use link state update packet and link state acknowledgement packet. I'm talking about the adjacency process. It's done. I'm sending a new information or periodic information after half an hour or 1 hour. And I use these two packets specifically for that purpose. So when we're going to see the update packets, it's going to carry multiple LSAs. It may carry LSA 1, 2, 3, 4, LSA 5, 7. So the idea is a single update packet is going to sum up all the LSAs inside of a single update packet may send it out. Point-to-point networks, updates are sent on 224.0.0.5. On point-to-multipoint network and virtual link networks, updates are unicasted. On broadcast networks, broadcast networks, because you see, I say, don't get confused. If an Ethernet network is broadcast, the screenshot that I showed you should have sent the hello packet, an update packet on 224.0.0.6. It's okay. Keep this question in mind. I'll explain in detail later, but short answer is, when you make this interface, let's say point to point, it's directly going to think there is only one possible neighbor on the other side, 224.0.0.5. Okay, because both of them are working on P2P design. P2P design. Cool. But if it's opposite, you have a switch and you have multiple routers connected here, everyone is going to process on this number. If I send any update packet on .5, everyone is going to receive that, and that's a problem for me. Rather, in network which is broadcast, in the broadcast network, what I do, I have elected a designated router, and designated router always listens on .6. Cool. So instead of sending the update packet to everyone and everyone is sending acknowledgement to me, I will let know only the DR, and only designated router is going to process, because as it is elected as a designated router, it is only processing .6 packets, or maybe also processing .6 packet apart from .5. And designated router's job is to send packets on .5. So it's going to let everyone know, including the router who sent the packet, by sending the update on .5. That's why, basically, if we, in context of Ethernet, it's not just Ethernet, but depends on the network types. Is going to depend where the update packets are sent out. We'll dive deep into it here later again, but generally understand that in point to point, the update packets are sent on 224.0.0.5. Okay, I explained this already. So this is what I was explaining. When you have a broadcast network, we are assuming that we're going to have multiple routers on that segment. Automatically, Ethernet is a technology that works on broadcast. This is a layer 2 link, and we have 5 routers available in here. To minimize the flooding behavior, the whole point, we had areas because we were trying to avoid that extra flooding. In here, again, the same thing is going to be, even though all these guys are in the same area, okay, flooding is coming again in the game. So to avoid that issue, in the broadcast type of network, there may be only 2 routers, but okay, we're not going to risk anything. It's an Ethernet network. That means it's going to work on broadcast. Automatically, in the two-way state, they are going to exchange the hello packets, or one DR router is going to be elected, designated router. And then a backup DR router, backup designated router is going to be elected. Their job is simple here. Election process is over, everyone is going to acknowledge. Here, rest of the routers are considered as a designated router or DR other. They only form full adjacencies with the DR and BDRs. With each other, they are stuck in a two-way state. That is why they're acknowledging each other. Hey, I know you are there. That is why if you go back a little bit, we had a different numbers for the neighbor count. Here, neighbor count may be 4 for one of the router, but the neighbor adjacency may be 2. Food for thought. Think about it. Whenever they want to send an update packet, a neighbor adjacencies only form the DR router, but whenever they want to form the adjacencies, they will only form with the DR. And when it times to send in any update, their updates are sent to everyone on this link. But I would say it's actually the DR and BDR are going to only those processing those .6 packet. The multicast address 224.0.0.6 is used by the DR and BDR only. And here, since DR is replying, BDR is kind of wait for 40 seconds if DR responds. If it's not responding, then this guy becomes a DR in this case. That's why we had a 40 seconds timer, a wait timer. So DR responds back with an update packets. So now, because their adjacency is only with the DR and BDR, they are going to process this information now. So instead of everyone sending like a madman to everyone, here the process one way. You send the packet to DR, DR sends on behalf of one guy, it's sending to everyone. So once the packet is sent out, the update packet is sent out, it needs to be reliably delivered. Okay, but by means of acknowledgement. There are two ways, and I found this information only in TCP/IP volume 1, is that there is going to be two types of acknowledgement. There's only implicit acknowledgement and explicit acknowledgement. Whatever LSA or update packet that is sent out, it needs to be acknowledged, and a receiving end is going to send out the duplicate copy of LSA. The one that I showed you when we saw the LS ACK packets was actually implicit acknowledgement. It was sending a whole copy of LSS. And then we have explicit acknowledgement, simply sending an acknowledgement instead of sending a duplicate copy of LSS. What we saw, we also had multiple LSAs. So in a one go, a single acknowledgement LSAs can acknowledge multiple LSAs. And it only sends the summary instead of sending the full copy, regardless whether it's an implicit or explicit. Do you understand this? Think of it like this. So here we have router 1, and here we have router 2. Now router 1 has sent us an LSA. Now router 2 have its own information. It's simply dumping back its own information. Router 1 sees its own copy, because this is how the database of router 2 was. Everything was synced already. So update packet sent by router 2 had information which was sent by router 1 originally. It is acknowledged. This is what I am, implicit acknowledgement. We're not sending any acknowledgement packet here. The update packet is acting as my acknowledgement here. Explicit is something, hey, this is not going to cut, because what you sent me was not actually same. So this is not going to consider as an implicit acknowledgement. You have to send me an LS ACK packet by acknowledging pretty much everything, by sending LSA headers of what I sent you, so that I know that you have actually received, for the purpose of acknowledgement. Now, each LSA 1, 2, 3, 4, 5, 6, 7, 8, or whatever the LSAs are, all the LSAs are going to have sequence number. Each LSA is going to contain these values, and that's how they know. I'm not talking about age, okay? Sequence number is something different. Each LSA contains some values that are used to ensure that the most recent copy of LSA exists in every database. If first copy is sent out with a sequence number of 1, it's fine. Second copy is sent out with 2. The receiving router knows that the most recent copy is 2, because what I have in the database is 1. If you clear IP/OSPF process, the sequence number is going to change, and you change certain parameters, you change network type. The new LSA needs to be sent out, because I want my neighbor to change their perspective, I want my neighbor to change their SPF topology so that everything will be in sync. And they can only do that based on the sequence number. So I will send a new LSA and increase the sequence by 1. So that's how the receiving router is going to judge, okay, what information I have is actually old. So I'm going to dump those information and only install what is sent out to me just now with a new sequence number. The sequence number is a 32-bit signed number. It's a linear value. You're going to see written in this manner. It's a hexadecimal value. See, unless a big network, you're not going to see values like this. But generally, it's written like this in hexadecimal. This is, as per the RFC, is called an initial sequence number. As per the RFC, the last it can go until is this value, max sequence number. So regardless, so I'm also going to upload this as a PDF, so you don't have to read anything. Just try to remember at least LSS theory. Secondly, just try to understand how flooding mechanism works, because this is going to help you in the troubleshooting. Flooding has the behavior I explained already. There are a couple of things that each LSA have: the sequence number, the checksum value, and the age. We are talking about the sequence of each LSS. Okay, so each LSA that is router is going to produce is going to increment the sequence number by 1. And if the present sequence number is this, which one? Max, which is last, we can't have more than this. The router needs to produce a number, first LSA. It must be creating a new LSA and flood to its all the neighbor, regardless if anybody have asked or not. Then each LSA, each routing information LSAs are going to have a checksum calculated. So okay, apart from your all the TCP level, excuse me, the IP level checksums, all those things, you still have a checksum calculated for the OSPF inside of OSPF separately. This is done by the process. They use a special algorithm called Fleischer algorithm, and they consider an output value of a 16-bit, which is injected. So basically, they take LSA, put it through Fleischer algorithm, whatever is value generated is put inside of the LSA header. When you say LSA header, it's like this. So hopefully I have some neighbors here. Do we have anything? Okay, I have something. So I'm looking at the database of router 10 itself. We are looking at the type 1 LSA. We are telling I want to look at the database. I want to look at the type 1 LSA of this neighbor, or even it's me, because all the neighbors are dead. When we say header, okay, this is the whole information of the type 1 LSA. What is considered as header? What you see inside of those DBD packet in exchange state is this, only this much information until then. Not even, I guess, number of links is also not included. You can check the packet. Until this, so this is inside of the DBD packet. Do you see what else we got? We have LSA. That means it is generated since 208 seconds. We have options. I explained option field also, right? You have this is a type 1 LSA. Link state is basically telling which router generated it, because generating is different. Maybe the advertising router is different. Why? Because ABRs may be advertising the routing information separately. We'll understand this behavior later. But do you see the sequence number? This is the 68th. Is it? That's the sequence number, and this is the checksum value. So this is how the checksum value is inserted inside of the LSA header. We'll interpret all this information. We'll come back to this topology. Let's finish one more thing. So each checksum of each LSS has to verify every 5 minutes. We didn't talk about the age. Under the interface there was INF transmit delay, right? Something on transmission delay. Under that, which was 1 second by default, which is saying if LSA is going out of that interface, it's going to be increasing its age by every 1 second. So age is here. We also have age. Okay, this LSA link state age. This LSA age is 208 seconds. Every 1 second is changing. Now it's 340. Look at this. Now it's going to change again. 344. Usually, when you don't go inside and just check the show IP OSPF database, you can also check the age here, the sequence number also. Look at this. This is why we're taking time to understand these things. Age, sequence number, and checksum is shown directly in the brief view, not in detail. Look at this. Each second is changing 68, 69, 70. And this is the timer that we saw. Show IP, OSPF interface, transmit delay, infra transmit delay. 1 second. So there is a behavior that if an LSA, I sent an LSA, they have a, by default, assuming we didn't change anything, their age is going to be max age 1 hour. After 1 hour, the whole LSA is going to be, this is the culprit, which everyone was fearing. Because of infra transmit delay, every 1 second, their LSA's age is going to increase by 1 second, or by 1. Because of that, after 1 hour exactly, it will reach the max age and the LSAs will be dropped. So the router is going to expect new LSAs flooded from the source. Okay. So if you talk about the LSA types, we have 3 LSA types. We have here type 1, excuse me, not 3, we have 11. Type 1, type 2, type 3. We also have type 4 LSA. These are generated by, again, I'm going to go in very detail about all these LSAs. Out of all these, we don't use type 6 LSA. We don't use type 8. And type 9 to 11 was specially designed for traffic engineering purpose. Maybe you might have seen it with MPLS. So our focus for enterprise design is going to be 1, 2, 3, 4, 5, and especially 6. Let's go ahead. Let's try to understand the type 1 LSA. What is it exactly? And how they actually behave. So I am going to just type our. So the design, the topology is, we have a data center and it has 4 main routers here, router 201, 202, 211, and 212. These are internal core routers. And there are data center, or say edge routers as well, DC router 1, DC router 2, router 6, router 4, DC router 4. DC router 1 and DC router 2 are at the edge. That's where the internet traffic exists. DC router 6 is connecting to site 6 where we have already EIGRP running. DC router 4 is connecting us to a site 4. And 201 and 202, these 2 routers are also connecting us to site HQ, where HQ have their own ISP. Because we will see, because in the objectives of the objective is there is a focus in path preferences. So we're going to play around with a different type of scenarios to prefer one path over another in different type of areas. So first of all, what I'm going to do, since this is a data center, we're going to enable area 0 here. Okay. Try to understand one thing here. Okay. These 4 routers, or more specifically, these 211 and 212. Let's understand their IP addressing scheme. Everywhere we are using 10.2. Okay. Okay. We have everywhere 10.2. But if you have a link, for instance, data center router 6. Okay, use that. It has 2 interface going towards site 6. It's using 10.6. So Ethernet 0/2 have 10.6.61.6. 61 has been going towards 61. Then 1/0 10.6, 62.6. This guy had membership with both routers. It's learning all the EITP routes already. Okay. All the subnets are in 10.6 though. That's the important part. Similarly, our data center router 4 have 2 interfaces, 1/0 and 0/2. No, this is supposed to be listing not to network interfaces. So we'll make, when we'll come here, we will fix that IP address. Okay. 201 also have, like, majority of the interfaces facing inwards towards DC, but one interface going towards this side, HQ. So if we go there, show IP interface brief, we have one interface, 1/2. Look at this. 10.1 because it's headquarter. 201 representing it's a link between HQ and DC that's coming from 201. Similarly, the link between HQ and 202, this will be 10.1.202. So we can confirm that here as well. 1/2. 1/2. 1/1.202.202. Hopefully everybody understood how the IP addresses are. And everywhere we have, at least majority of the places we have the loopbacks. 10.2. And they all follow the same design. 10.x, x represents the site number, 255 is in the third octet represents the loopback, and y represents the device number itself. So definitely you can guess DC router 1. This is site number 2. 10.2.255.1, like this. Anyway, let's start now. First of all, we'll focus these two guys, 211. Okay, we don't have router OSPF 1, network 00. Yes, yeah. Show IP OSPF. OSPF is enabled. Show IP OSPF interface brief. So because of the command, we have enabled OSPF everywhere. That is fine for 211 because we are not facing any interface on the other areas. Let's go to 212. This guy. I think I should change the. That is better. One. Let me. Okay, here router OSPF 1. Router 212 have neighborship with 2 routers. Router 6. We can. You guys are not able to see it.
Yeah, can speak to that. But it's outsourced with the
Can you see? Can you see now?
yes, yes, yes.
Okay. I'm quickly going to copy paste the router. So on router 6, we inform the neighborship. With router 211, we form the neighborship. Let's go to not able to see the interfaces names here. Okay, I'm going to go to DC router 1 first. So 4 routers outwards, 4 routers inwards. DC router 1, DC router. I already have enabled in the command. 201. Yes, we can, because I'm only matching 10.2. So only inward interfaces towards DC is going to enable those. Let's go. Let's do DC router 4 as well. We'll fix the IP address. Don't worry about it. What else we got? 202 is done. 201 is done. So let's pick the easier one. At the moment, the data center router 1 have 2 physical interfaces. You have 2 physical interfaces. So we will go ahead and look at, let's go to 212 on this router. Or even let's go ahead with on the router on here, 201. So we know that we are looking at the router information a little bit ahead or further. We're checking our show IP route OSPF. So we can check that we have all these standard 2 routes that we have learned just now. Let's do show IP OSPF database. When you execute this command, well, it's telling us that this is OSPF router with ID 10.2.255.201. That's router ID. What process are you running? And these are your type 1 LSA. You assume directly that all these routers are part of the same LSA where you are executing this command. This router 201, they are part of area 0. So you see, if 201 was in area 1, let's just say, not ABR, not in area 0, but area 1, you will only see all the router LSA of area 1 only. So by looking at the router IDs, or here, link ID means different things in different LSAs. Here, it's their router IDs. It is router 1, router 2, router 4, and router 6. Outward, 4 routers. And inward, a data center, we have 4 routers. Switched router 201, which is us, 202, 211, and 212, including our own information saying who's advertising it. It's also mentioning how many seconds it's been we have received that information, because we recently enable OSPF. Let's check some. This is okay. I forgot to remove OSPF on router 6. So router 6 was the router where we already had the OSPF running, and that's why the sequence number is huge for router 6. 65. How, and not only that, it is also fascinatingly saying that how many LS or links we have in OSPF for that neighbor. So what does that mean? We said earlier that router 1 had 2 interfaces, and third one is loop back in router 1. To IPOSPF interface brief. This is different than DC router 1. Oh, I guess. Let me go to DC router 1 then. To IPOSPF interface brief. 3 interfaces. Loop back 0/2 0/1. Okay. Go back to 201 again. On the surface area, we are seeing there are 3 links. We take out this. Okay, since we're talking about only router LSS, the type 1 LSS, show IPOSPF database. To check the details of type 1 LSA, we type router command followed by the router ID or the link ID. So now whatever you see is this data center router 1 LSS. Okay. So this is the header. What else we got? This is the router links. It's saying this is a type 1 LSA. Link state ID, router ID, advertising router ID, sequence number, checksum number. The length, as the links will grow, the length will also grow. As a summary, it says that you have 3 interfaces. So somebody sent 201, this router 201, an LSA, type 1 LSA of data center router 1. And it had 3 links. Each link's state is also separately given. This is the detailed information sent in the update packet upon asked using the link state request packet. This is the header packet. This is the header of this LSA, and this is the detailed information. So if you remember that, so here's the thing, okay. What do you see? This is a link connected to a stub network. So I know there are 2 things possibly. Either it's a loop back, or it is an interface where you don't have any OSPF neighbors connected. You don't have a neighbors connected. Okay. So a stub network. Its IP address is 10.2.255.1. Okay, so it's safe to assume, I'm going to just pick. Interface loopback 0. IP address is 10.1.255.1 and /32. It is also telling the network mask here. Now, I really want you to understand and focus here just for 5 minutes. If you move on to the next link, this is a really big aha moment, and I understood actually why the hell they were creating type 2 LSS. Okay, let's move on to the next interface. This is the stub network that we understood. If you understand the next one, this interface is 10.2.11.211. No, it's actually, it's just telling us about the link. It's not telling us about any kind of interface. It's simply a transit network. Okay, this is the transit network. It means that on this link we have OSPF running routers that have formed adjacencies. That's simply it. And on that link, you may have multiple routers, but on that link, there is a DR router that have formed, that have become the DR router, and its IP address is 10.2.11.211. So it's simple for me. Now I know that on this link, there is a DR. This is the first router, 10.2.11.211. This is the first router. Okay. And the router itself, that router IP address was advertising, we are looking at its LSA, its IP address on that link is this. So at least now I have a one interface in mind that has this IP address 10.2.11.1. Now what it does, it also now know if there is any other LSA, that have this IP address. But before that, it will ask one question. Immediately when you have a designated router, that means designated router's job is to generate type 2 LSA. I'm moving away from subject just for a minute. Designated router's job, the type 2 LSAs are only and only are generated in broadcast networks. Okay, broadcast networks. If you don't have broadcast, it will not generate type 2 LSA. Please understand that. So this link here, at least this link, because based on the IP address, okay, this is the link, 211 DC router 1. 211 have won the election on this link, Ethernet 0/1. We can verify that as well by going to 211 and check Ethernet 0/1 should show as a DR on the local interface. Ethernet 0/1 will show the local state. What is state? This is the link state is a DR, designated router. So automatically router 211 is going to generate a type 2 LSA to explain how many routers are there in this link. And it will send it to other neighbors, assuming that it got to 201 where we were here. So if you check the show IP OSPF database, type 2 LSAs is called network LSAs. First of all, let's check general LSAs. Okay, this is your router LSAs, and where is it? Okay. So this was our DR. Okay, this was our DR that generated that LSA. So the link ID for that LSA will be the same. It's not going to be the loopback of generated router. It's not going to be. Look at this. This is a type 2 LSA. We assume that link ID is going to be that. No, link ID will be the IP address of that, because it's not the router who are generated. And the DR is not representing the whole router. It is possible that on this link, router 211 may be the DR other. So it's not safe to say that it is for the whole, the representation is for the whole router. It is representing only that link. So in this moment, this is going to be the link ID for type 2 LSA. And you can see, if I simply say show IP OSPF database network, do not put the link just like you put here, right? In the type 1 LSAs, the link IDs were router IDs. In type 2 LSAs, the link IDs are the actual IP address of the interface which are DR elected. So we take this and we type this. What is it saying? Here we understood based on the, if we go up a little bit, when we looked at the type 1 LSA, here it was showing the network mask. But from this link, how would the router know what is the network mask? Because it's simply telling how many routers are in the link, because this is why it's interesting. OSPF now knows who's the DR. It connected a link to the type 2 LSA. And in the type 2 LSAs, what do we see? This is network LSA generated by, look at this, 10.2.1.212. This is the interface. This is the interface we're talking about, transit interface. Type 2 LSA generated by advertising router is someone was 212, but the link ID is supposed to be the IP address of that link address. IP address. And it's saying that the network mask is /24. So if for instance, if the DR would not advertise this type 2 LSA, router 201 would not know the subnet mask of this network, the transit network. So it connects this type 1 LSA's link, not the whole LSA, but the link of that LSA is connecting with the type 2, because that contains, and if you have multiple routers in that link, it will show all the attached router, not just 2. Because there are only 2, you are seeing only 2. And in that, so now I know from this that these 2 routers are connected with each other, and there are so and so routers are available on that link. So if you go back a little bit, this is 10.2.255.211. This is 10.2.255.1. I also understood this is a /24 because I connected it back to the type 2 LSA. The subnet of this link is 10.2.11.0/24. So at least I explained you in that detail, but at least I have a small topology where I have router 211. They have a link with router DC router 1. I don't know what interface address is, but what I understood is that they have connection with each other, and where DC router is the DR, and there's this subnet is basically 10.2.11.0/24. Do you guys understand how actually the SPF topology is created? Everyone? Vijay? Hey, I think it's a little bit too much.
Yeah, but we need to practice this thing.
Okay, here's the thing. What happens if this network was, let's say, a P2P? I will take this thing again in detail. Let's go ahead and data center router 1. I said IP OSPF network point to point. Stable established neighborhood. That's the router 211. IP OSPF point. Now here's the thing. We now know we already had three links in here. But if I check the same LSA from DT's data center router 1, it's going to tell a lie here. Now this link, which was considered as a transit link, is going to be different. Okay, here's the thing. Now it became a point-to-point link. That point, what is the meaning of point-to-point? There are only 2 links, 2 routers on that link. So, okay, it's immediately advertising that link. And now no, this is 211. One router is 211 on that link. The other router is this guy, router 1. Cool. But what about, since we do not have, look at this. Earlier it was saying the designated router, but now it's simply saying neighboring router and the local router whose LSA we are checking. That's all. Where is the subnet mask? What is the subnet itself is simply telling us the link. It's simply telling us which router are there. It's not telling us which subnet it is. So it's telling a lie. When you make a point-to-point interface, in the broadcast network, type 2 LSA was serving a big purpose. Here, it's not going to be there is not going to be a DR, hence there is not going to be generating any type 2 LSA. It says immediately there are 4 links. Earlier it was mentioning that there are 3 links only. Right? Look, Same LSA we are checking. This here we're saying designated router and mentioning the subnet. And when we check the type 2 LSA generated by the DR, it was showing the detailed information. Now, what it does, when you make a point-to-point interface, it counts two links. One link for the topology, where you mention which router is neighboring router, and what is the local IP address. That's all. That's all. But for the sake of advertising the routing information, which because of the lack of type 2 LSA, it's going to advertise a stub network. You see? A stub network with the subnet information. Link cost is going to be the same as this link cost. Okay, let's see. We also have 10.2.1.212. That means this link was the link from router DC router 1 towards DC router 211. There is one more link. It is going towards DC router 212. We can make that link also. Okay, this link Ethernet 0/1, Ethernet 0/1 on both sides. We go to DC router 1 first. To 12. IP OSPF network point to point. Cool. So let's go back to this guy again, 201, and let's see what he thinks. Now we were seeing this as a transit network. It will show two more. It will count two links for the same thing. Now it became
Five.
5. No, it should become 6. Excuse me, from 4 to 6, right? Let's see.
5. One is this.
Oh yeah, you're right.
5.
It's 5 because one link is a stub network, which is a loopback. This both links means this is a one interface because it's a point-to-point. It is generating two links there, and just from looking at it, we can kind of draw a diagram. Well, not we wouldn't know which interface it is, but at least we would know what router on that link it is and what is the subnet they have. Look at this 10 dot. This is the 212 neighboring router. This is the local IP address of that link, and they are advertising a stub links, stub network separately to advertise the whole network with subnet mask. Since we don't have a type 2 LSA of that link, do you guys understand the relation between these? Everyone?
Just a little scroll.
That's all. We don't have much. Okay, guys, this is gonna be too much here. Let's wrap it up for today. Let's continue the next session, and I'll start from LSA 1 again, and I'll try to explain it a little bit differently. Hopefully, you guys can understand. Type 1 and 2 are the fundamentals for like rest of the LSAs. Otherwise, you'll not understand. Because you see, these links will be LSAs never are converted into type 3. These links will be converted into type 3. AVRs look at these links only to understand how they are actually generating type 3 LSAs in order to understand the links. And so far, we understood the stub network, we understood point-to-point network, and we understood transit network. So these are the three states you will see of the links in type 1 LSAs. Any questions? Okay, guys, thank you. I'll see you tomorrow. I'll see
Okay, thank you.
next week. Bye.
I'm having few questions I will post into the chat.
Please do. I'll be waiting. Thank you. Hey, Rick. How are you?